Welcome. In this video, we will begin our study of differential calculus, a fundamental branch of mathematics with wide-ranging applications. By the end of this session, you will be able to define and calculate average rates of change, understand the concept of instantaneous rates of change, and use the limit definition to find the derivative of a function. We'll start with an opening problem to build an intuitive understanding of these concepts. Let's consider a simple scenario. Adding water to a container at a constant rate. The depth of the water will increase over time. First, let's think about the graph of the volume of water added against time. Since the water is added at a constant rate, the volume increases by the same amount in each unit of time. This means the relationship between volume and time is linear. Therefore, the graph of volume versus time is a straight line. Because we start with no water at time 0, the line passes through the origin. What does the gradient of this straight line tell us? The gradient is the change in volume divided by the change in time. This is precisely the rate at which water is being added to the container. So the gradient represents the constant rate of flow. Now let's think about the graph of the depth of water against time. This is where the shape of the container becomes crucial. Consider a cylindrical container. As water is added at a constant rate, the volume increases linearly. Since the base area of a cylinder is constant, the depth must also increase linearly. The volume is simply the base area times the depth. So if volume increases linearly, depth must also increase linearly. This means the graph of depth versus time for a cylinder is a straight line. The gradient of this line would represent the constant rate at which the depth is increasing. Now, let's look at an inverted conical container. As water is added, the water level rises. However, the surface area of the water is not constant. It increases as the depth increases. To add the same volume of water, the depth must increase by a smaller amount each time. The rate of change of depth is not constant. This results in a curved graph for depth versus time. The curve is concave down, indicating that the rate of increase in depth is slowing down over time. This is a key insight. For nonlinear relationships, the rate of change is not constant. This leads us to the core idea of rates of change. A rate is a comparison between two quantities with different units. For example, speed is a rate of change of distance with respect to time, measured in meters per second or kilometers per hour. A typing rate is words per minute. These are all examples of rates. When the relationship between two variables is a straight line, the rate of change is constant. The gradient of the line gives us this constant rate. For instance, in a distance-time graph, the gradient of a straight line segment is the constant speed of the object. However, as we saw with the conical container, in the real world, rates are often not constant. They vary over time. To deal with these changing rates, we need a more powerful mathematical tool. This tool is differential calculus. Differential calculus is the branch of mathematics that deals with rates of change. It allows us to analyze how quantities change, even when that change is not constant. Let's formalize the idea of an average rate of change. This is the first step towards understanding instantaneous rates. In most real-world situations, rates of change are not constant. For example, the temperature of a glass of water left in the sun will increase, but not at a steady pace. It might increase quickly at first and then slow down as it approaches the ambient temperature. In such cases, we can calculate the average rate of change over a specific interval. This gives us a general idea of how much the quantity changed per unit of time over that period. For example, if the temperature increases from 5 degrees Celsius at time t equals 0 to 20 degrees Celsius at time t equals 2 minutes, the average rate of change is the total change in temperature divided by the total change in time. That's 20 minus 5 divided by 2 minus 0, which equals 7.5 degrees Celsius per minute. Let's connect this to the language of functions. If we have a function y equals f of x, the average rate of change from x equals a to x equals b has a specific formula. The average rate of change is given by the formula f of b minus f of a, all divided by b minus a. This formula should look familiar. It's the same formula we use to find the gradient of a straight line. On a graph, this average rate of change is the gradient of the chord connecting the 2 points on the curve, a at a, fa, and b at b, f of b. Let's work through an example to solidify this concept. Consider the function f of x equals x squared. We want to find the average rate of change from x equals 1 to x equals 2. Here, a is 1 and b is 2. First, we need to find the corresponding function values, f of a and f of b. F of 1 is 1 squared, which is 1, and f of 2 is 2 squared, which is 4. So our 2 points are 1, 1, and 2, 4. Now we apply the formula. The average rate of change is f of 2 minus f of 1 divided by 2 minus 1. This gives us 4 minus 1 divided by 1, which is 3. The average rate of change of x squared between x equals 1 and x equals 2 is 3. This value, 3, represents the gradient of the chord connecting the points 1, 1, and 2, 4 on the parabola y equals x squared. Now we move to the more complex but crucial concept of instantaneous rates of change. This is the rate of change at a single specific instant. Think about the speedometer in a car. It shows your instantaneous speed, the speed you are traveling at that exact moment. It's not an average over a journey. It's the rate of change of your position at that instant. How can we find the rate of change at a single point on a curve? We can't use the average rate of change formula directly because we only have 1 point, not 2. We need a way to get infinitely close to that point. This is where the idea of a tangent line comes in. Let's investigate this idea using a falling object. Suppose the distance dA ball has fallen after t seconds is given by a function, which we can graph. Let's pick a fixed point f on the curve, say at t equals 2 seconds. Now let's pick another point m, say at t equals 4 seconds. The chord connecting f and m represents the average speed over the interval from 2 to 4 seconds. The gradient of this chord is the average speed. If f is at 220 and m is at 480, the average speed is 80 minus 20 divided by 4 minus 2, which is 30 meters per second. Now, what happens if we move point M closer and closer to point F? Let's see. Imagine we have our fixed point F and our moving point M. We've calculated the average speed for M at t equals 4. Now, let's move M closer to F. Let's try t equals 3. The chord FM is now steeper. The average speed is higher. Let's try t equals 2.5. The chord is even steeper, and the average speed is even higher. As M gets closer and closer to F, the chord FM approaches a special line that just touches the curve at point F. This line is called the tangent to the curve at F. The gradient of this tangent line represents the instantaneous rate of change at point F. In our example, it would be the instantaneous speed of the ball at t equals 2 seconds. So, the instantaneous rate of change is the gradient of the tangent. We can use this geometric interpretation to find instantaneous rates of change from a graph. We simply draw the tangent line at the point of interest and find its gradient. Let's look at this example. We have a curve, y equals f of x, and 2 tangent lines are drawn, one at point A and one at point B. To find the instantaneous rate of change at A, we find the gradient of the tangent line at A. This line passes through the points 0, 2, and 2, 4. The gradient is 4 minus 2 divided by 2 minus 0, which is 1. So the instantaneous rate of change at A is 1. Similarly, to find the instantaneous rate of change at B, we find the gradient of the tangent line at B. This line passes through 4, 2, and 5, 0. The gradient is 0 minus 2 divided by 5 minus 4, which is negative 2. The instantaneous rate of change at B is negative 2. While drawing tangents is useful for visualization, it's not precise. We need an algebraic method. This brings us to the formal definition of the gradient of a tangent. We start with our average rate of change formula. Let's rename the points. Let the fixed point be A at A, FA. Let the moving point be B at A plus H, F of A plus H. Here, H represents the horizontal distance between the 2 points. The gradient of the chord AB is F of A plus H minus F of A, all divided by H. This is the same formula as before, just with different notation. To find the instantaneous rate of change at A, we need to make point B get infinitely close to point A. In our new notation, this means making the horizontal distance h approach 0. We do this using a limit. The gradient of the tangent at x equals a is the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. This is the fundamental definition of the derivative, and it's a cornerstone of calculus. Let's apply this powerful definition to find the gradient of the tangent to f of x equals x squared at the point 2, 4. Here, our function is f of x equals x squared, and our point of interest is where x equals 2. So a equals 2. We substitute a equals 2 into our limit definition. We need to find the limit as h approaches 0 of f of 2 plus h minus f of 2, all divided by h. Now we substitute the function f of x equals x squared. F of 2 plus h is 2 plus h squared, and f of 2 is 2 squared, which is 4. Next, we expand the numerator. 2 plus h squared is 4 plus 4h plus h squared. Subtracting 4, we are left with 4h plus h squared. We can factor out an h from the numerator, giving us h times 4 plus h. The h in the numerator and the h in the denominator cancel out as long as h is not 0. Since we are taking a limit as h approaches 0 but h is never actually 0, this cancellation is valid. Finally, we can substitute h equals 0 into the simplified expression. The limit is 4 plus 0, which is 4. The gradient of the tangent to f of x equals x squared at the point 2, 4 is 4. This process of finding the gradient of the tangent can be generalized. For a nonlinear function, the gradient of the tangent changes as we move along the curve. We can define a new function called the gradient function or derivative function, which gives us the gradient of the tangent for any given value of x. This gradient function is called the derivative of f of x, and it is labeled f prime of x. It is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Let's find the derivative function for f of x equals x squared. We follow the same steps as before, but we keep x as a variable. F prime of x is the limit as h approaches 0 of x plus h squared minus x squared, all divided by h. Expanding the numerator gives x squared plus 2xh plus h squared minus x squared. The x squared terms cancel, leaving 2xh plus h squared. Factoring out h and canceling gives the limit as h approaches 0 of 2x plus h. Substituting h equals 0, we find that the derivative function is f prime of x equals 2x. This is a powerful result. For any point x on the parabola y equals x squared, the gradient of the tangent at that point is simply 2x. For example, at x equals 3, the gradient is 2 times 3, which is 6. Let's recap what we've learned. We started with the idea of average rates of change, which are the gradients of chords. We then extended this to instantaneous rates of change, which are the gradients of tangents. We saw how to estimate these from a graph, and, more importantly, how to calculate them precisely using the limit definition. This led us to the concept of the derivative function, f prime of x, which gives the gradient of the tangent for any x. This is the foundation of differential calculus. You are now equipped with the fundamental tools to understand and calculate rates of change, a skill that is central to IB Mathematics AAHL. To help you master these concepts, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then check your solutions. Question 1. The distance s in meters of a particle from a fixed point at time t in seconds is given by s of t equals 2t squared plus 3t. Find the average speed of the particle over the interval from t equals 1 to t equals 3 seconds. Question 2. The graph of a function y equals f of x is shown. By drawing a tangent, estimate the instantaneous rate of change of f of x at x equals 2. Question 3. Using the limit definition of the derivative, find the derivative of f of x equals 3x minus 5. Question 4. The volume 5 in cubic centimeters of a sphere with radius r in centimeters is given by v of r equals 4 over 3 pi r cubed. Find the average rate of change of the volume as the radius increases from 2 centimeters to 4 centimeters. Question 5. Using the limit definition of the derivative, find the derivative of f of x equals 1 over x. Let's go through the solutions. For question 1, we need to find the average speed. We use the average rate of change formula. First, find the positions at t equals 1 and t equals 3, s of 1 is 5, and s of 3 is 27. The average speed is 27 minus 5 divided by 2, which is 11 meters per second. For question 2, we need to estimate the gradient of the tangent at x equals 2. We draw a tangent line at x equals 2. This line appears to pass through the points 0, 1, and 4, 5. The gradient is 5 minus 1 divided by 4 minus 0, which is 1. So the estimated instantaneous rate of change is 1. For question 3, we use the limit definition for f of x equals 3x minus 5. F prime of x is the limit as h approaches 0 of 3 times x plus h minus 5 minus 3x minus 5, all divided by h. Expanding the numerator gives 3x plus 3h minus 5 minus 3x plus 5. The 3x and 5 terms cancel, leaving 3h. The h's cancel, and the limit is 3. The derivative is 3. For question 4, we find the average rate of change of volume. We find the volume at r equals 2 and r equals 4. V of 2 is 32 pi over 3, and V of 4 is 256 pi over 3. The average rate is 256 pi over 3 minus 32 pi over 3, divided by 2, which simplifies to 112 pi over 3 cubic centimeters per centimeter. Finally, for question 5, we find the derivative of f of x equals 1 over x. F prime of x is the limit as h approaches 0 of 1 over x plus h minus 1 over x, all divided by h. We find a common denominator in the numerator, which is x times an x plus h. This gives us x minus x plus h over x times x plus h, all divided by h. The numerator simplifies to negative h. We can then cancel the h's, leaving negative 1 over x times x plus h. Taking the limit as h approaches 0, we get negative 1 over x squared. The derivative is negative 1 over x squared. That concludes our introduction to differential calculus. We have covered the essential concepts of average and instantaneous rates of change and the formal definition of the derivative. You should now be able to calculate average rates of change, understand instantaneous rates as the gradient of a tangent, and use the limit definition to find the derivative of a function. These skills are foundational for the rest of your calculus journey. Thank you for watching.